Now we're going to talk about steel making. We're revisiting the flow diagram for steel processing. And where have we been so far? We've been through iron making, where iron ore was reduced through either the blast furnace or what we didn't really talk about that much, direct reduction of iron. Now we're at this point where the iron is ready to move into the steel making process, the purpose of which is to remove the carbon and to alloy. And we're going to look at these two processes right here first, the converter and the electric arc furnace. We'll start first with the basic oxygen furnace for steel making. Scrap can be added. This is scrap to the basic oxygen furnace. But the main additive that we need here is the iron, the pig iron, from either the blast furnace or the direct reduction process. Oxygen lance is lowered, oxygen is blown in, the carbon comes off with the as CO2 with the off gases. The steel is tapped off, and then the slag can be poured out. Secondly, here is electric arc furnace. Electric arc furnaces are very popular in the United States because we have a lot of scrap, and scrap is the main input for the electric arc furnace. You see the electrodes being lowered, an arc is drawn, the scrap is melted, the steel is tapped off the bottom of the furnace, and then the slag is removed. So there are several different types of basic oxygen furnace. Here's a top blown basic oxygen furnace like we saw in the previous animation, and here's a bottom blown basic oxygen furnace. Basic oxygen furnaces serve two major purposes regardless of their configuration. They remove silicon, and the main purpose though is to remove carbon, and they do it very quickly. That's part of the attractiveness of a basic oxygen furnace. From about 4% carbon within about 20 minutes, reducing the carbon content to almost zero. Here we see silicon being reduced in even shorter times. Phosphorus and sulfur can be reduced as well. Those contents, those are undesirables. And manganese is also lost. Now manganese and silicon may be added back in later depending on the alloy. Since this class is about microstructure, let's pause again here to talk about what the microstructure would look like if we made our line pipe out of the product at this point. After the basic oxygen furnace, we've removed almost all the other elements other than iron. So there's no alloying elements, no solid solution strengthening like that would come from elements like manganese or silicon. There's no second phase that would come from the iron carbide, the pearlite. What we're seeing here is almost pure iron in the ferrite phase with very large grains. This scale bar is 0.5 millimeter, so some of these grains would be almost visible, if not visible, with the naked eye. This would be a very weak product. You would not want to make a pressure holding product like a line pipe out of steel with this microstructure. Now we're going to talk about the secondary refining processes. Where are we at in our steel processing diagram? We're in the latter part of steel making, the secondary refining processes. Here's a diagram of the most common type of secondary refining processes, and that's the ladle metallurgy furnace, where alloy additions can be added from a hopper, stirring is conducted, and gases can be blown in from the bottom. that carry with them the tramp elements and the bad actors like hydrogen, oxygen, some of the other gases. And then heat can also be added at this point to prepare for casting using the electrodes. To demonstrate that there are various types of secondary refining, here firstly we have an animation of vacuum degassing where a snorkel is lowered to the ladle and low pressure circulates the liquid steel up into an argon atmosphere to reduce the carbon, hydrogen, nitrogen, and oxygen, which can be bad actors in the steel product, and prepare for desulfurization. Secondly, we got a refining station diagram here where the liquid steel can be stirred, oxides can be removed, calcium, aluminum, and other alloying additions can be added, and also a ladle metallurgy furnace that can reheat to prepare for casting, add alloying additions. You see here, alloy systems can be added, fed in by rod to dephosphorize and desulfurize to remove those bad actors for the product. Now deleterious elements have been removed, desired alloying elements have been added, our liquid metal is at the right temperature, and we're ready for casting. We're at this stage now in our steel processing flow diagram. For years, steel was cast into ingots before being formed into the final product. But over the past half century, continuous casting has increased and now dominates at about 95% of steel production. You see the ladle filling the tundish fills the molds. The outer surfaces solidify in the molds, and then the steel strand descends from the continuous caster and then is cut to form slabs, and those slabs can be further rolled, which is applicable for the seamed products that'll be formed into pipe and tube and then seam welded, but is not applicable for seamless tube. And so in the diagram below, we see strand casting that can then be formed into tube rounds for seamless pipe making. Since ingots have been so important for so many years for steel line pipe and for metals casting in general, let's take a look at what microstructures can form in the ingot itself and how those might affect the downstream microstructure. So if we start with the image on the left here, in brief, the zones for an ingot begin with the chill zone, which is where solidification would begin. Along the mold wall, there would be very fine grains. Then the columnar zone, where the grains are larger, visible to the naked eye here. And then closer to the center line, there's fine grains again that formed most likely heterogeneously out of the liquid. And a pipe is typical, this is called pipe, due to solidification shrinkage, and porosity can also exist in the last metal to solidify. Since steel is so important, steel ingots specifically have been studied in depth, and the segregation of steel ingots specifically is important because of the effects it can have on the final product. So here in a diagram of a steel ingot, you see the columnar zone growing inward, and then heterogeneous nucleation, where you see these grains, and that the heavier grains would lead to a certain type of segregation. And so let's move over to the diagram on the far right, and we see where the author of this research has specifically broken down the regions of segregation that can be expected in a steel ingot, with the cone of negative segregation with the heavier elements showing up near the bottom of the ingot, A-channel segregates, and V-channel segregates. And those have all been classified. And then a location where due to solidification shrinkage and the escaping gases from the solidifying ingot, there can be um, segregation and gases, inclusions and voids up near the top of the ingot. As we conclude this video on steel making, let's review the process and see how we've added value at each stage. We started with the iron ore, and we made iron by reducing the oxides. Then we made steel by removing the carbon and adding the desired alloying elements. And then we solidified the material by casting. If we look at what we did to the microstructure through this process and how we added value, firstly, in the liquid iron, there would have been a lot of those carbides due to the high carbon content, oxides, silicates, and other inclusions, and a generally dirty product that would have been low strength, low toughness. So we turned that into steel by removing a lot of those impurities, reducing the carbon, and we made pretty much pure iron before our secondary refining. But that would have been a really soft product, pure, but really, really soft and low strength. So we added alloying elements to that, and now I've jumped forward and I show two microstructures here, one for vintage and one for example for modern pipe, just so you can get an idea of what we do to the grains later in the product. And so you see for both of these, the grain size is much smaller. For vintage in the micrograph, you can see grains. For modern, you can barely see the little grain boundaries in there. So you can see that as we work through this process further, we're going to see more differences between vintage and modern steels. And you can see the dark regions would be the carbide, the iron carbide and ferrite regions that we call perlite. And those perlite regions and the fine grain size are a couple of the strengthening mechanisms for our final pipe product. And we're going to talk later about different strengthening mechanisms for modern alloys. After steel making, the next step in the process is pipe making.